Hey guys, welcome to this sort of online, I guess, recitation sort of thing I'm doing. Essentially what I want to do here is just have these videos up for you guys to study with, and to review some of the concepts you've been looking at in your class. So in chemistry there's a lot of concepts and a lot of math and a lot of ideas that have to be put together to properly get ideas right and get problems right on tests and homework, and get further on when you take MCATs and study for advanced degrees and things like that. It's important to have all these this base knowledge very sound, and one of the best ways to do that is just by the amount of time you can see it and interact with it. Unfortunately, we're very limited on the amount of time I get to see you or your professor gets to see you. So what I thought is, if I did these little online videos, perhaps that would give you a little more exposure to topics and things like that. So what I'd like to do is just do this. If you guys like aspects of it, let me know. If you dislike some aspects of it, let me know, and I'll try to change accordingly. If you have any suggestions or questions, feel free to ask those as well, and I think it would be great to interact with you guys, so that way I can learn what best way to teach you through this process. And it's sort of exploratory, so at the moment I might not have the setup sort of concrete, and it might change from a video to video. We'll see, depending on what works and what doesn't. So hopefully you guys get something out of this. For the moment, we're just going to start right where your class started and work from there, and hopefully you guys enjoy it. Alright, thanks. I'll see you guys in the video. Alright guys, so here we are with our first virtual lesson. It's going to be over for Intermolecular Forces, and going to tell you a little bit more about them so you can better understand what's going on with each one and the differences between them. So first I'd like to explain a few concepts, and we'll actually go over some problems that you would see on these forces. So here's some of the conceptual stuff that we've been looking at. So intermolecular forces are effectively the attractive forces between molecules. When we think about perhaps a HBr molecule and another HBr molecule, within a large system they will be attracted to one another, and we have to wonder, why does this happen? Well, there are multiple different attractive forces that we've talked about in this chapter, but essentially the main three are London dispersion forces, dipole-dipole interactions, and hydrogen bonding, which is sort of a dipole-dipole interaction, but I'll get more to that later on. So let's take a look at each of these in order. So first off, van der Waals and London dispersion forces. These are the weakest forces, and I'd like to explain a little bit about this to you guys. So let's assume we have two molecules, two atoms even, just for thinking about this in simplicity's sake. And let's say they have 3 valence electrons. So ignoring their core electrons, we have 3 electrons in their valence shell. So sometimes what can happen with these molecules is, since these electrons have a probability to be in certain areas, so if we think about Schrodinger's equations and things like that, Schrodinger distribution of electrons, they aren't always going to be in the same place, and they're in fact always going to be moving around the molecule or atom. So when we think about this, they could all shift perhaps to one side at one moment. We can't tell if this is going to happen, but we know it can happen. So when that occurs, we'll actually end up with some sort of dipole moment. So you can see here on this atom, I've labeled that this dipole would have a net positive dipole on the left side and a negative dipole on the right side. So what that means is we'll have some sort of electrostatic interaction with other things around it. So it'll actually occur, since this atom here has a net dipole, it'll affect other atoms. So this other atom that's located close to it on the left will also shift in order to balance out the charge that's set upon it. So here you'll see now we have a net negative dipole close to the net positive dipole. What this gives us is it makes this it makes this more stable, and this process will occur naturally and actually forms a bond between these two, since we have this slight negative charge and this slight positive charge. So that's essentially van der Waals forces. They're also van der Waals and London dispersion. It's the same name, in case you guys didn't know. It's just two ways to say the same sort of forces. They're essentially electrostatic interaction from polarized electrons. What I mean by polarized electrons is the idea that the electrons that were once separated on the molecule polarized to only one side. So all the molecules that were once surrounding this molecule all ended up on one side, or at least a majority moved to one side, causing a dipole to occur. So the ability of a molecule or an atom to polarize increases with size and molecular weight. So that's usually how we think in class. If you look at two materials that have similar London dispersion forces, if one's higher in molecular weight, it's going to have stronger London dispersion forces. So we can consider it the stronger intermolecular forces overall, if that's the only thing we're looking at. And the last thing to think about is, since this is sort of looking at electrons moving to one side of a molecule causing a net dipole to occur, if you have a higher surface area or a longer chain molecule, so if we have a very long organic molecule versus a large clumped up one, you'll have more London dispersion forces because you can have a greater polarizability. So that will increase your van der Waals / London dispersion forces as well. So that's pretty much it for that. Let's move on to the next interaction. The next interaction we're going to look at is dipole-dipole interactions. So these interactions are more based on actual charge distribution in a molecule, not looking at induced polarizability. So here we have two HBr molecules from the beginning, and we know they have a bond together. We know they kind of interact, but how is this? Well, if we think about it, they should have dipoles on them. Now, unlike van der Waals forces or London dispersion forces, this isn't caused by a shifting of electrons to one side or another based on random movement. This is actually because of electronegativity. So here you can see electronegativity on the periodic table. So bromine down here has a higher electronegativity than hydrogen, which lies up here. So therefore, we should see the bromine attract more of the electron density towards it and away from the hydrogen. This will leave us with a positive dipole on the hydrogen with a negative dipole on the bromine. This will cause an attraction between the positive and the negative dipoles, which gives us this dipole-dipole interaction. Pretty simple. So this is essentially an electrostatic interaction, but it's caused by electronegativity, or in some cases you can even see a charge difference. For example, if you do the balance charges on a Lewis dot structure, and you notice that some molecules have a positive, or atoms have a positive, and others have a negative, those will likely contribute to dipole-dipole interactions for intermolecular forces later on. So that sort of combines multiple concepts. So that's pretty much it for dipole. Let's look at hydrogen bonds. Alright guys, so hydrogen bonds here. These are essentially a very specialized form of dipole-dipole, but let's get into this. So if we think about the classic molecule when we think about hydrogen bonds is of course water, so H2O here. So we're left with two hydrogens and one oxygen. If you draw the Lewis dot structure, however, you will see that you have two free electron pairs. So I've shown those here by these purple clouds that essentially represent the electron pairs. So what will occur is, since we have an electronegativity difference between hydrogen and oxygen, we'll end up with a positive dipole on hydrogen and a negative dipole on oxygen. And along with that, we have a huge electron cloud over here, so we have an even more negative dipole over here and a positive pole on the left side of the molecule. So we have a very large concentration of positive on the left, while a very low a very high concentration of negative over here by these electron clouds. So these hydrogens are very positively they have very positive dipole. So what happens when another water molecule comes into play is that it will actually interact in the same way. So each of these hydrogens would have a positive dipole on them. So what can happen is this positive hydrogen will be very attracted to the oxygen, more specifically the free electrons that are floating on that oxygen. And so you'll actually see this in multiple compounds, including oxygen, nitrogen, and fluorine are the most common bound hydrogen, because they have a lot of these free electron clouds floating around that can easily bond to other hydrogens. So that's what you would expect to see from hydrogen bonding, and it's actually one of the most, it's actually the strongest interaction that you find in these intermolecular forces. So let's just compare a little bit between these. You guys should probably have seen this before, but just to make sure it's concrete in your heads. So the differences in strength between these materials. So at the beginning we have London dispersion forces. These are the weakest forces. Because they only have an induced polarizability attraction, there's not really a strong positive and negative to each molecule. They're very weak positive and negative, so they do provide some level of attraction and interaction, but not very strong. Keep in mind, however, if you have giant molecules, these can have a lot of interaction. For example, a lot of organic materials like cell bilayers and just long fatty acids or things like that, they have a ton of London dispersion forces, which actually give them pretty decent interactions. But they're still probably a lot weaker than these other interactions by themselves. So the next sort of interaction that's stronger than London dispersion is a general dipole-dipole. So this is caused by a difference in electronegativity, as we sort of already said. So we have a distribution of the electron density a lot of the time. So we'll have a lot of electron density on one side of the molecule and a lot less on the other side. This will cause a difference in dipole moments, so we'll have positive and negative sort of dipoles on them, causing an attraction. This is a lot stronger than London dispersion. And even further than that, we'll have hydrogen bonding, which essentially is a combination of this dipole moment on the hydrogen and whatever we're bonding to, whether it's oxygen, nitrogen, or fluorine, and in interaction with that and the huge electronegativity of that oxygen, nitrogen, or fluorine because of their free electron clouds, free electron pairs that can interact with that huge positive dipole on the hydrogen. So hopefully that helps you guys a little bit with these interactions and intermolecular forces. Here I'm going to pull up a few problems that we're going to work through together, and what I suggest is you guys try to do them before I do them, and then go through and make sure that your thought processes were correct and you get all the correct answers. That way, you know, you can use it as sort of a test to see if you're doing all right. Alright guys, so this is the sort of format I'm going to try to use. You can see me here in the corner. Hello. Just so, you know, you guys can see me. Maybe I don't know. I feel like it's more personable that way. Maybe I'm crazy. But, so the first set of problems here, you guys should be able to see them on the screen, is essentially just labeling the intermolecular forces of these 6 compounds. So when we think of intermolecular forces, you have to think of a few things. So, oh, my parentheses are amazing. Let's undo that. Let's actually just type it. So, intermolecular forces, we have what? London dispersion. We have, along with that, we have dipole to dipole interactions and hydrogen bonding. So we need to label these 3 type of intermolecular forces within the following system. So looking at this first compound, how do we start off thinking about these systems? So a lot of the times, actually, in order to label everything properly, it's a good idea to draw out the systems. So just to draw one of these out, I'm going to show you here. There's oh my gosh, my drawing will be awful. Oop. Boom, boom. So here we're going to put our carbons down the middle. And so you guys would probably want to do the Lewis dot structure if you actually want to observe the exact setup of this, but that's essentially, I've done this enough to where I know the Lewis dot structure of these materials. If you have any questions or want to see a review on that, ask me, and I will definitely do it. But for now, I'm just going to write it out because that's not what we're focusing on. So you can see here that we have a carbon backbone with hydrogens essentially sitting on one of the carbons and the fluorine sitting on the other ones. So when we think about this sort of material, we can immediately sort of eliminate hydrogen bonding, because we don't have like an OH bond. A carbon-hydrogen bond does not work for hydrogen bonding, so we don't have to worry about that. Next thing we kind of look at, we can look at London dispersion. So pretty much everything is going to have London dispersion that you look at. In this case, we can have essentially polarization of this molecule anywhere along these outer sort of species. So this one will definitely have London dispersion, intermolecular forces. Lastly, we want to look at dipole-dipole. So let's see here. These three fluorides here are very electronegative, we know, because they sit at the top right of the periodic table, while these hydrogens are not going to be as electronegative. So I would guess that we're going to see a sort of dipole like this, which would mean that in a big system of a bunch of these materials, that fluorines would probably be attracted to these hydrogens. So I'm going to guess we're going to see dipole to dipole interactions. Okay, so that's the first one. Pretty easy, huh? So let's move on to the next guy. Alright guys, CCl4. This one's not too bad either. So just to get started, let's draw out the Lewis dot structure. So essentially what this one's going to be is just a tetrahedral system with the carbon at the center and the chlorines on each of the domains. So you can see here that we have a pretty uniform system. It's actually very symmetrical. So that immediately eliminates dipole-dipole, because if we have a completely symmetrical system like this, there would be no dipoles existing in the overall net dipoles, essentially. Hydrogen bonding, we don't have any hydrogens in this, so that seems unlikely. And lastly, London dispersion, well, everything can have polarizability, so we'll go ahead and throw that on there. Let's look at the next one. Alright guys, so SO2. SO2, sulfur dioxide, is a little tricky. So if you guys remember back to Lewis dot structures and things like that, I have to make sure I'm not drawing on my face. I'm not. Alright, so sulfur, we're going to connect it up to two oxygens. Each of these would have, you know, these surrounding electrons, which we wouldn't worry too much about. But we need to use up 18 electrons. So actually the way to do that is to get rid of these two, double bond, do that. And that actually gives us the lowest spread of charges. So with this sort of setup, we end up having a negative charge here. Oop, there's my undo button, there it is. We end up with a negative and a positive charge here, okay? So when we do it like this, you can easily see first off that we have dipole-dipoles, because we have a large positive charge here and a large negative charge here. So immediately we can say that we have dipole to dipole interactions. And of course we always have London dispersion. Since we're looking at this, well, it doesn't look like we have any hydrogens, so we don't have to worry about that one in this case. Alright, let's look at the next one. Bromine fluoride, well, this one's actually pretty simple. So if you think about it, it's just a bromine connecting to a fluorine, like this. Well, we definitely have a dipole because fluorine's super electronegative. So we're going to have a slight dipole like that. So we're going to have dipole to dipole. And also, we always are going to have London dispersion, even though I can't draw now. Alright, next one. Let's look at this next compound. Alright guys, so the next two compounds really exemplify why we need to have, why we need to draw out the structures sometimes. So here, let's look at this compound. So we have 3 methane groups on the nitrogen. So you can see here, if we draw out the Lewis dot structure, we should have a carbon, carbon that way, and these all have hydrogens on them. Oh my gosh, this is going to get really sloppy. I apologize. This has a hydrogen. This has a hydrogen. Hydrogen. So the interesting thing is these don't really matter that much, these hydrogens, because since they're symmetric around this thing, we're not going to see too much issues. However, if you notice here, we actually, if you count up the number of electrons that we have in the system, we actually have 2 more. So we have to put them on this nitrogen. So we have a, that's bad. bad putting them on there. So we actually end up with this electron lone pair. So since we have this electron lone pair, we have a huge negative bias up here at the top. So we end up with both London dispersion for this guy and also dipole to dipole because of this huge negative region up here. So that will cause us to have a large dipole. Now, lastly, we have this compound here, this phosphorus pentachloride. So here, let's see, if we do the Lewis dot structure, we end up with boom, boom, Cl, Cl, and we also have this setup. So if you guys did the Lewis dot structure correctly, you should notice that we actually have a trigonal bipyramidal setup, which means that we are completely symmetrical and we have no net dipole amount about the structure. So we end up with just London dispersion forces. So what I want to emphasize here is that first off, you guys should be able to figure these out on your own at this point. Always draw out the structure if you're not sure about whether or not you have dipole-dipole interactions or anything like that. So that's what the main emphasis of these problems sort of were. I'll see you guys in the next one. Hey guys, so the next thing I sort of want to look at is comparing the intermolecular forces between multiple compounds and being able to pick what has stronger forces and what has weaker forces. This kind of has play because that'll affect, what has a higher boiling point, what has higher vapor pressure, what has a bunch of other physical properties are based off of these intermolecular forces, so we kind of want to be able to compare them between one another. So starting over here on the left, we have these three compounds we're going to compare. So starting out with HBr, this material, first off, has London dispersion forces. So we can immediately get this one off the list, on the list, I guess. Another sort of thing, since we have bromine and we have hydrogen, and they have very different electronegativities, it's likely that we're going to have dipole-dipole interactions here. So we would say that this material has both dipole-dipole and London dispersion. So looking at oxygen here, O2, we can think about it first off that it has London dispersion. The difference between it and something like HBr is that since we have a symmetric molecule, and it's homogeneous, there's not going to be any dipoles between the two materials. So therefore, we're not going to have any dipole-dipole for the O2. So we can instantly get rid of that. Lastly, there's no hydrogen in here, so we definitely don't have to worry about that. For this methanol compound, we can see that first off, we should have London dispersion forces. Along with that, it's most likely that we will have dipole-dipole because of these, this CH3 and the OH, they're not balanced. So you're going to end up with some dipole-dipole forces, probably not as many as you would for HBr. But along with that, since we have this oxygen to hydrogen bond, we're going to end up with hydrogen bonding, which is a major contributor. So if we want to put these in order, it's going to end up being CH3OH with the largest, so that one's the biggest, followed by HBr with dipole-dipole interactions, and O2 with the least intermolecular forces. So when we think about this, it's pretty interesting because O2 you have as a gas, so we can instantly sort of see, like, yeah, it should be weakest, because since we have a lower boiling point, it would make us a gas, which means lower intermolecular forces. Those all sort of tie together. That's what I want you guys to see with that problem. So the next one is the same general idea, so let's go ahead and look at it. So iodine here and nitrogen are both simple atomic materials. They're completely homogeneous, so there's no dipole interactions, so these are both going to just be London dispersion. We sort of already talked about that. You guys all know H2O. It's pretty much a staple that it is London dispersion. It's going to have dipole-dipole, and it's going to have hydrogen bonding. Lastly, hydrogen sulfide here. We're going to have London dispersion. We also will have dipole-dipole. But since we don't have an O bonding to an H in this case, or nitrogen, then we're not going to see those hydrogen bonds. So this is not going to have these hydrogen bonds like H2O does. So putting these in order, we can obviously go like this. We know H2O is going to be our highest with these hydrogen bonds. Since H2S has dipoles, we can assume that's higher than the other two. And then so now we're stuck. Do we look at I2 or N2 as stronger? Well, at that point we have to start looking into molecular weight. Since I2 is heavier, if we look at the periodic table, then I2 is going to have stronger forces. Than N2. So like that, this would be our order for this problem, and I hope you guys understand that. So if you get to a difference between two compounds, they have the same type of forces, you look at molecular weight, and that's sort of something you guys probably already knew, but I just want to emphasize it. Alright, so that pretty much sums it up for intermolecular forces. I hope you guys got a lot out of this video. Please let me know what you got out of it, either through email or talk to me if you anyway, in class or lab or whatever. I'm thinking about doing more of these. Let me know if you guys have any ideas of what you want me to cover, if you have specific problems you want me to do, or if you have particular topics you want me to cover, because I'm hoping to do this in supplement with my other sort of teaching methods for you guys, and end up teaching you guys a lot, hopefully. So thank you all for watching, and I'll see you all on the next one.